this is going to be a session that covers quite a broad arc. We will take off with control engineering, dive into the strange world of synthetic biology before moving into the fields of dreams of bioenergy, and finally come to a hard stop at a concrete wall. So with that, I would like to invite our first speaker, and this will be Dr. Mario Garcia Sanz, who is one of the newest program directors at ARPA-E. Mario?
Thank you.
So, let's just...
Good afternoon, everyone. Thank you very much for coming. I am actually the newest one, I think, at ARPA-E, the newest program director. I would like to talk to you today about one of the things that is really, has been one of my passions for more than 30 years, that is related to control engineering. And I would like to start with a question, a quick question for you, a fundamental question. So, we tried to fly for many years. We had just, in the fast pitch session, some examples about, planes and electric planes, but we tried to fly for many, many years. And my question for you is why the Wright brothers succeed? Why did the Wright brothers succeed? Actually, you can be thinking that maybe it's because of the very interesting and advanced airfoils that they put together, maybe because of the, the experiments in the wind tunnels. I would like you to see, an answer, in the area of control. So I really think that, in my opinion, it's because they use control concepts in the design of the system. So actually, the plane of the Wright brothers is a plane with very small wings at the front. Because of this, we actually change, the place of, the relative position of the lift and the weight, and then the plane itself tends to overturn and, quickly, go, upside down. So they did this because they realized that they needed a plane that was very fast, reacting with wind disturbances in order to be able to fly. So this is actually a control concept, that they find this idea, and the plane is actually unstable. So they also, put a control system to stabilize the plane. So control was in the very beginning of the thinking of the system. And by putting these small wings, they were able to be, fast enough, to reject the disturbances. Another very interesting example is the very first, and this is now energy, the very first wind turbine that we had, for electrical generation. That was actually in Cleveland, Ohio, 1887. And the engineer that put this together was Charles Brush, one of the pioneers of the electrical field. One of the things that he did is also to incorporate these control ideas. It was actually a huge system, more than 17 meters diameter, 144 blades, but one of the keys was, the incorporation of a rotor control with a yaw control system, and that allowed the system to be working without any problem for over 20 years. So again, control at the very beginning of the design of the process. However, we are not in the same situation today. So many of our universities, and actually, the way we study engineering today is very specialized, because, technical systems are more and more difficult, so we have to specialize, but we have now a narrower picture. So it's more difficult, to work as these pioneers, as the Wright brothers or, Charles Brush and other people did in the past. As a consequence, we have a sequential way of working generally in companies, so when we have a problem, we first of all design, maybe let's say if it's a wind turbine, we design the aerodynamics, the mechanical structure, then the electrical problem, the electronics. And at the very end of the picture, we ask the control engineers to develop the control solution, the control algorithms to control the system automatically, maybe with PIDs or things like that. And this way of thinking, this way of working is actually limiting the possibilities to have an optimal design at the end. So my idea, for this fast speech today is just one thing, that is to go back to this multidisciplinary concurrent engineering way of thinking, putting control concepts from the very beginning of the design of the system. So we have to have all the engineering departments working together, the mechanical engineers, the electrical engineers, the aerodynamics engineers, thermodynamics, whatever we have, with the control engineers as well, with the economics, with the operation and maintenance, with the regulations, with the standards, with the certification, everything in the same table, working together, and actually incorporating the control engineering concepts, things like dynamics, feedback, stability, the things that actually the Wright brothers, put in the picture, to be successful. In this way, we will be able to reach optimal designs in many areas. A couple of examples, and are actually personal examples I was involved in the past, quickly. One is about, wind energy. I remember, a project, and that was the end of the 90s, that I was involved in a multi-megawatt wind turbine design, and by designing a better pitch control system, that you move the blades, to control the rotor speed, we actually reduced a lot, the mechanical fatigue of the tower, and we were able, to have a much cheaper tower, even about 30% cheaper than the competitor that was, putting together a machine of the same size at the same time. So this is control at the very beginning, helping us to have a much better design at the end. Another project I was also involved, same period, was about a water treatment plant for a city, a big city. Usually water treatment plants, you have actuators, like this one that you can see in the picture is for nitrates and ammonia removal. So you have, like 3 actuators working continuously with the same set point, typically depending on the temperature. So you have like 3 or 4 different set points over the year. So you have internal recirculation, external recirculation, and other things like that. So if we incorporate, sensors, feedback, and control, we will be able not only to improve the performance, but also to reduce the cost of the installation, the infrastructure, and this is a very big thing. So with all these ideas, I would like to propose a potential new ARPA-E program that will be around these fundamental concepts about concurrent control engineering. And this ARPA-E program, and I really like your feedback about this, but will be, a program, to bring together, many different communities, mechanical engineers, electrical engineers, bioengineers, chemical engineers, all kind of, engineers, control engineers, economics, et cetera, and so we will need, this new philosophy, to design the systems. We have probably, to end up with some mathematical formulation of how to incorporate the dynamics, the feedback, the control into the picture. We need probably, special sensors or new actuators, distributed sensors, optimization algorithms, taking into account things like artificial intelligence or maybe machine learning, and all these things, ending up in a computer program to do the optimization. And obviously, this is all across all energy applications. You have here in the picture, something about water treatment plants, including desalination systems, including digesters, networks, also, hydrokinetic energy, wind energy, either, conventional onshore, offshore, floating wind turbines, flying wind turbines. Also the grid, we can design the grid in a new way, for microgrids, large grids, et cetera, conventional generation, solar systems, etc. So this can be, eventually a new ARPA-E program, and I really would like, to have your feedback, in this area. So thank you very much. And I would like now to introduce Victoria Chernow, that is a fellow at ARPA-E. So thank you.
Thank you, Mario. So before we go to Victoria, I just quickly wanted to remind you, and if we can switch over to the instructions for questions, I forgot to mention that, if we could switch the slides, please, to show, so I'm sorry, I didn't. So remember, the number here for this session is 70748, and you text that as the first number to 22333. And then really important, you only have 160 characters. Anything else gets truncated. In the last session, there were a number of questions that couldn't be answered because they didn't arrive in a fully intelligible form because they got cut off. So you will see this slide probably briefly in between all talks, so feel free to send your questions anytime you have them. So let's make sure that we get a good set of questions for the end and for the discussion. And with that, Victoria?
So, hi everyone. I kind of want to switch gears a little bit and talk about microbial synthetic biology, and more specifically, how we can think about strategies for using synthetic biology in order to produce energy-relevant materials, structures, and processes. So let's start by talking about microbes. So these particular microbes that we see probably look pretty adorable, but I think in general, we tend to associate microbes with disease. However, if you've ever enjoyed yogurt or cheese, maybe a glass of wine or beer, perhaps even some kimchi, then you have the need to think simple single-celled microbes for that. Without microbes like lactobacillus and yeast, none of these delicious treats would be available to us. And so, despite the relative simplicity of most microbes, especially compared to multicellular organisms, microbes have evolved over billions of years to solve challenges in areas as diverse as catalysis, material synthesis, carbon fixation, and energy harvesting. And that includes photosynthesis, but also older metabolisms that rely on the redox reaction of metals. Additionally, biological systems in microbes allow for self-replication and self-repair, as well as complex self-assembly. And so we can imagine that if we can harness all these vast biological capabilities of microbes, we can start developing technologies that could be potentially unparalleled, not only in their low cost, but also their deployability. So we also are luckily living in an era where researchers have figured out ways to engineer microbes specifically to produce unique types of products and materials. And so one way that we can envision doing this is by very precisely designing what genes we want our microbes to express. We can then synthetically build this DNA, insert it into a host cell, allow the cell to replicate, and in the process produce the various materials and products that we desire. In fact, synthetic biology has matured to such a point that we're already seeing commercial efforts in areas like algae-based biofuels, pharmaceuticals, and even specialty chemicals. But with such a rich technology to work with, synthetic biology, I want to ask, what more can we do with this particular technology? Specifically, I want to ask, can synthetic biology help us generate materials, structures, and processes that were previously thought to be impractical or maybe even impossible using biology? And so one area that I want to think about is electronic waste. So in 2016, the US alone produced about 6.3 million metric tons of electronic waste. And globally, about 80% of this electronic waste gets either landfilled or incinerated. So without even considering the energy input necessary to build these electronics, just purely focusing on the material side of things, recovering the metal from 100,000 phones, which is really not that much, recovering this precious metal will yield about 5 pounds of gold, 2,000 pounds of copper, and 55 pounds of silver. And right now, all of these materials, all these useful materials, are simply either sitting in a landfill or being systematically destroyed. So, knowing that certain microbes can actually participate in the redox reaction of metals, I want to pose the question, can synthetic biology make recycling of electronic waste practical? So instead of incinerating or landfilling these electronic materials, what about designing or synthesizing microbes that can actually act in a bio-leaching capacity, can bio-reduce metals, and we can do this for the entire spectrum of metals. So going from precious, rare earth, even abundant metals. And what about also engineering microbes to potentially recover plastics or aid in landfill remediation? So in some sense, I think this scheme gives us an idea of how we can use synthetic biology to tear electronics down. But what about also using synthetic biology to build electronics back up? So can we also exploit additional biological facets like nanoscale manufacturing precision and self-assembly to create complex molecules and nanostructures that first might be too cost prohibitive to make synthetically, and secondly, could be made in outside the confines of an energy-intensive clean room facility. So we already know that microbes like bacteria are capable of making complex nanostructures like nanowires. So could we potentially envision using these sorts of pathways in order to create an entire gamut of new nanostructured materials for next generation electronics? And can we furthermore do this in a way that we can build them outside, again, outside of energy-intensive clean room facilities? So this is one scheme for making nanostructures. But what about also using synthetic biology to make more macro-scale materials? So recently, synthetic biology has also allowed us to engineer microbes that can secrete very specialized extracellular materials, essentially creating highly functionalized biofilms. So I want to ask, can we very specifically tailor the type of biofilms that we create in order to generate membranes and films that possess the gamut of properties, including programmable adhesion, maybe even electronic and optical properties? And what about programmable material properties? If we're able to do this, is this perhaps a pathway that can allow us to make ultra-cheap, high-performance, tailored membranes? If this is perhaps a pathway to do that, that could have huge implications in the area of industrial separations. So currently, separation processes account for about 16% of the total US energy consumption. And about half of separation processes currently rely on distillation. If we were able to replace about 90% of distillation with membrane-based separation, this would allow for about 7 quads of energy to be saved annually. This is a huge amount of energy. But currently, there are several barriers to the adoption of membrane-based technologies. Namely, many current state-of-the-art membranes are incredibly expensive. A lot of them can't tolerate harsh conditions like high temperatures, pressures, and extreme pH. Furthermore, most of them are susceptible to fouling. But interestingly, microbes have been generating biofilms for generations that can survive in the harshest of terrestrial environments. They can survive high temperatures, high pressures, high salinity, even survive in extremely acidic and basic conditions. So I want to posit the question, is maybe one future direction for industrial separations going to be due to synthetic biology? Can we possibly use biofilms for these purposes? So ultimately, I want to ask, what breakthroughs need to happen in order for synthetic biology to really revolutionize our energy landscape? And I want to pose this question to you. What innovations are necessary for synthetic biology to produce materials, structures, and processes that, first off, can behave with superior performance relative to their non-biological counterparts? Secondly, I want to ask, how can we make all of these materials, structures, and processes at minimal cost relative to the state of the art? And finally, how can we manufacture these things with a marginal energy input? So I really do think that your feedback is key, and I hope to hear all of your ideas. So please ask your questions, leave comments. I'm excited to hear what you have to say. So with that, thank you. And I would like to bring up my colleague, Dr. Mark von Keitz, to give his fast pitch. Thank you.
Thank you, Victoria. Okay. Good afternoon, everybody, and I would like to continue this theme on synthetic biology, but with a slightly different twist. So, as Victoria already said, there's a lot of advances in synthetic biology, and I really wanted to see how can we harness this synthetic biology potential in such a way that we can really maximize its impact on bioenergy. And to start with, I really want to remind everybody that biology already leads really with regard to CO2 capture and utilizations away. Every year, plants, terrestrial and marine together, fix 210 gigatons of carbon directly from the air. And we actually, for the fossil release is about 10 gigatons of carbon a year. So there's really a big carbon flows, and a lot of this carbon is actually captured and stored in various forms of carbohydrates, be it wood, grains, starch. And these carbohydrates, we have actually learned over the millennia by now to actually convert them with usually fermentation processes into beverages, chemicals, and fuels. And so, as I said, this is something that we have done quite a bit, and really in the last 40 years, particularly with molecular biology, we have been increasing our abilities and our flexibility. And then synthetic biology, with building new pathways from the bottom up, is starting to give us access to an incredible portfolio of products that we can make for chemicals and fuels in particular. So this is really something that is taking off tremendously. And not only do we enhance the diversity of products that we can make, but we can also make them better, more efficiently, and in part we really organize these oftentimes simpler cells by putting in compartments, putting enzymes together on scaffolds. So we end up actually with wonderful biocatalysts. And what do we do then? We stick them in the same old tanks. So it turns out they're not all that old, so we've gotten a little shinier over the years. But principally, we are still not quite measuring up to the potential of the engineering capabilities for the organism. We still basically take fermenters, bioreactors. They are meant to keep them happy. So usually microorganisms need a steady food supply, constant temperatures. They like a constant pH. You see a lot of these parameters follow the optimum curves, and you try to keep it in that range. And so we have developed pretty sophisticated fermenters, actually, where we can have a sensor that tells us what is the pH, what is the temperature. Are we running out of oxygen, for example, and then we can start pumping things in. But the way it works is typically that we have to mix it with a lot of power. It's usually quite a complex system, and it's really driving up the cost of the operation, in particular when we are going to scale, because then mixing times become very long, and we really don't get the maximum potential out of it. And so, most importantly, we are really not taking full advantage of the microorganisms. So what that leads us to is really, is there a different way on how we can think about bioprocesses? Can we make them cheaper, more robust, and particularly scalable? And so I want to challenge you with an image. This is actually a fermenter. It's a reactor. It's a silage pile. This is probably one of the most simple fermenters that you can imagine. And it's big. If you see at the lower right corner, that's a little tractor. So it's actually a full-size tractor. So it's really, really big, but it also has some challenges. You can't really mix that thing very much other than with a shovel, and that takes a long time. Maybe you can take the tractor, but that's still not really an effective. So you have to start thinking about how do I control that, but also how can I maybe adapt my microorganisms to live and respond to that. So, and in that point, I really enjoyed conversations that I had with Mario about when he came to the agency, he brought this concept of concurrent control engineering. And when I learned about that, I felt that that was really an interesting opportunity to integrate these things. So looking at that as a central paradigm that allows us to look simultaneously at the engineering of the biocatalyst as well as the reactor design, and really see how can we do this together and come up with novel solutions that take full advantage of the organisms, but also give new room to the reactor engineering that hopefully is driving down cost and driving up performance. So just to further round this out, one of the things in a pile like this, what you need is you can't get by with one sensor and hoping that your material is going to swim by there once every 5 minutes. So distributed sensors would make a lot of a difference. But then again, just knowing that you have the pH here at a certain value, if you can't respond to it, you need to have a distributed actuator concept. So the interesting part would be biocatalysts are not like typical chemical catalysts. They are responsive. And so what they can do is they can potentially be even the distributed sensors and the distributed actuators. So it really opens up a lot of new paradigms of how we think about an integrated process design. And other parts that you also see in biology, and for example, the rumen of the cow, that's very, very effective. But one of the things it does, it actively removes products to reduce inhibitory effects and actually drives the equilibrium forward. Another part, and that's really pushing it even one level further, is that we are looking not only at one individual cell type that is working throughout the reactor, but if we have heterogeneities in our systems, we might want to respond to that with heterogeneities in the populations of cells that we are using. So there might be, we either might look at differentiating ourselves or using consortia that are working together on different parts. So these are just ideas of where this could go. The fundamental question is really, what are your ideas and how can you reimagine bioprocessing? I think this is a conversation that we would like to start. We believe that there are tremendous opportunities, but we are also really looking for your input, for the communication with you. And with that, I would like to thank you very much and would like to turn it over to my colleague, Dr. Joe Cornelius. Thank you.
This is advanced.
Yep. And I think I've moved it forward to yours, so you should be able to see it.
Okay, let's really mix it up. We've gone from microbes, I'm going to talk baseball. I know this is March Madness week, but I'm from St. Louis, and we don't have a basketball team, so we kind of talk baseball year-round. What I really want to emphasize here from a agricultural production of bioenergy and baseball, that we live in a big data arena. And for those of you who are not familiar with the movie or the book by Michael Lewis, Moneyball basically is a story about how the Oakland A's were able to use data analytics to fundamentally pull an entire industry from an analog managed by the gut age into the digital age, where data analytics actually became a very critical component for success and failure. Now, from an agricultural standpoint, 2% of the energy that we produce ends up going into our agroforestry system in the form of fertilizer, irrigation, mechanization, pest control. It's a fairly hungry industry as it relates to energy inputs. But it also produces, as a consequence of that, not only all the food we consume, but also 5% of the energy that goes back into our energy system. And there are unintended consequences. 99% of greenhouse gases come from agriculture, and it uses over 80% of our fresh water. So as we think about baseball and agriculture, what do they have in common? Well, first, both actually exploit the expertise of a general manager that is on the field, basically making management decisions and guiding that team to success or victory. The other thing they have in common, in the springtime, everyone is a series contender. When you start your season, you believe that your team's going all the way. The other thing that they have in common is that every field they play on is different environment, different challenges, and it's routinely heard by baseball fans and farmers alike that when the season ends and they were a little bit disappointed, the statement, "Wait until next year." Well, with agriculture and the planetary challenges, next year is actually getting is becoming more critical for us. And Branch Rickey once said that baseball is a game of inches. Well, it's now a game of nanometers and milliseconds. And having tools such as in sabermetrics enabled baseball to actually go digital. As we think about the convergence of technologies in the 21st century, data analytics actually provides us with massive opportunities in this space as we think about bioenergy production and agriculture in general. We believe that it's achievable for us to actually be able to double productivity, to significantly cut our emissions by at least in half, to reduce the resource demands that agriculture imposes, such as in nitrogen, or fertilizers in general, and water, and all at the same time be able to provide a much deeper and more robust pool of renewable fuel options that would help serve this nation and do it in a sustainable way. Now, the Department of Energy and the USDA have done numerous analyses, and what's particularly interesting about one of those key analyses, the billion-ton study, was the realization that we do have the capacity. Actually, the U.S. most significant strategic asset is the fact that we have 1.5 billion acres of cropland, pasture, and forestry with the potential to produce 20% of our energy needs. But we have to increase our yield gain. We actually have to achieve the same yield gains that we realized during the Green Revolution, and they are clearly within our grasp. The good news is that opening day, the day that we actually plant our crop, that is the time when we have our greatest genetic potential. That's 100% genetic opportunity. But every day after, nature takes a bite out of the yield. And if we use the very best management practices, we're able to achieve approximately 30% of the genetic potential. So we basically give away 60% of the yield just to our inability to manage environment to its optimum. And if you look at the national average, it gets even more, actually, I guess the opportunity is actually even better in the context that producers are at 10% of the genetic potential. They achieve about half of what the best management practice is because they're not optimizing the decisions. So if you look at agriculture, it is a game of inches. Thousands of decisions are being made on the field every day in a sub-optimal way, and those decisions add up to 60% yield losses that we observe year over year. So what we're pursuing is actually a program that actually, on a scalable way, is looking at developing high-efficiency production systems that harnesses data sets that we can collect in the field. The primary problem we're trying to fix is that every field is different. Every game is different. And in that field, we're trying to manage microclimates, soil, pests, water, all these variables in a very complex way. And we now have tools that actually allow us to be able to start collecting those particular data sets, and we have new ones that would be coming along. We believe that distributed intelligence is a key attribute for our being able to realize these genetic gains, but distributed intelligence with a difference. This isn't the IoT that we are currently familiar with. We're talking about delivering distributed intelligence to western Nebraska, where it's a long way to run an extension cord all the way out there to the field. So we have to have systems that are able to actually be able to deliver power in a very affordable, accurate way. We're looking for new sensor modalities. We're looking for data analytics that actually provide real-time knowledge. Data for data's sake means nothing. We actually have to create tools that actually create things that are operable in the field. And we're really enthusiastic about a lot of cutting-edge frontier platforms that are coming together in sensor, power, analytics, and communication capabilities. Lab on a chip, where we're able to actually measure a plant's metabolic health on a real-time basis. Using plants as electron harvesters themselves. Computers the size of grains of sand. At the end of the day, we have to harness all of these tools so that we're making the right decision at the right time, every time. Failure is not an option. And integrating all these systems and inventing novel innovations along the way, that's ARPA-E hard. And we're asking for you here today and your networks to actually help us think through what a program like this in this particular space would feel like. What I want to leave you with is one final quote from Michael Lewis. One absolutely cannot tell by watching a batter the difference between a great 300 hitter and an average 275 hitter, because that difference is only one hit every 2 weeks. We fundamentally believe by digitizing ag in this particular space, we can transform our ability to actually create a no-compromise bioenergy solution. Thank you.
Hi, I'm Joseph King, and I'm going to talk about something that's so fundamental that we all take it for granted. I'm going to talk about cement, concrete, and the infrastructure. Now, my engineering friends have been pushing me for years to get into something big, something in the material space. And since I look at engineers as kind of the oxen that pulls society ever forward, I take their comments to heart. That's why I picked cement. It's not big, it's bigger than big. The largest produced material on the planet, and second only to water in terms of consumption. So, quick review. You take limestone, mix it with a little gypsum, pyrolyze it, you get cement. Take cement, mix it with water and aggregate, get concrete. Take concrete, and that is the vast bulk of the material used in our infrastructure. Now, when people look at cements and concretes and try to improve its energy profile and greenhouse gas production, they usually look at first the kiln. Why? Because that's where the energy is imparted and 90% of the greenhouse gases come from. But modern kilns are extremely good at what they do and highly efficient. So a lot of people then move further upstream. So they're doing everything on the front end, and that is coming out with materials that, although incredibly clever and good at what they do, are what I refer to as an awful lot of sizzle for very little steak. And what I mean by that is there's a volume issue. So much cement is produced annually that for them to ever grow their businesses large enough to make even a marginal impact is almost impossible. It'll take decades upon decades. Last year alone in the US, we produced 130 million metric tons of cement. Globally, it was 4.2 billion metric tons. So, when you look at this, you might say, okay, Joe, great. What are you going to do? Well, I'm going to look at the back end, post-production, but change it up a little bit too. And that is, if you can increase the durability of the cements and concretes you make a factor of 2 or 3, you de facto diminish the embodied energy over time for that structure. So it's a different way of looking at reducing embodied energy and greenhouse gas production by improving the durability of your materials. Now you might say, well, why are you looking at infrastructure? Well, first off, it's the biggest use of cement and concrete in North America, actually the world. Secondly, we all say those same bad words when we see that our mamas told us never to say. We see road work ahead signs, or we hit a bump on the road like on 66, 295, or the Inner Beltway when they aren't being used as parking lots. Anyway, so third, it's a totally nonpartisan issue. Liberals and conservatives, Democrats and Republicans, independents and libertarians, well, maybe not libertarians, but the vast bulk of the herd gets that a properly functioning infrastructure benefits us all. Why? Because we feel it in our daily lives, and when we commute to work, and when we travel with our families. Now, some groups, or some countries actually, understand this and get this. China, for instance, in just 2011, 2012, and 2013, produced and consumed 50% more cement than the United States did in the entire 20th century. Think about that. That was our greatest infrastructure growth period. So, you might say, okay, Joe, nice history lesson, but what are we like today? Well, we're not doing so well. This is our report card from the American Society of Civil Engineers. And it's going to cost us a fortune, plus an amazing amount of energy over the next 5 to 7 years, just to continue our current Band-Aids and tourniquets approach to managing our infrastructure. So you might say, well, Joe, is there a solution to this? Absolutely. Imagine the Capitol building. It took its current form in the mid-19th century when Thomas Walter, the fourth architect of the Capitol, expanded it out to allow for all the new states joining the Union, more than doubling its size. And then he capped it with this dome that is built in what is known as the wedding cake style. This dome is almost 9 million pounds of cast iron. Some of you may know this building, the Pantheon in Rome. It's 2,000 years old. It too has a dome. However, its dome is 100% unreinforced concrete. And in fact, this dome is in fact 50% larger than the Capitol's dome. So, you might say, that's interesting. Well, no modern engineer using contemporary materials would dare to build this structure this way today, which is why even 2,000 years later, it's still the largest unreinforced concrete dome on the planet. In fact, this building is so pristine, it's been in active use for the last 2,000 years. This other building, no one's really sure how often it's actively used. Now, you might say, what's the difference? This is the Great Hall of the Markets of Trajan, actually built before the Pantheon, but out of the same materials, probably the same union workforce. And what you see when you look at it is it's kind of a dog's dinner of stuff all mushed together. But using modern analytic and spectroscopic techniques, what you see when you look at it is also kind of, well, a dog's dinner of stuff mushed together. But to a trained spectroscopist, mineralogist, or material scientist, what you notice immediately is there is no microcracking. And in fact, you see a lot of structures in there and elements that are unique and not common to any contemporary cements and concretes. Microcracking happens almost immediately in modern cements and concretes, and it is a prelude to the ultimate demise of those structures years to decades later. So, what can we do? First is, can we do and replicate some of those structures and minerals that we saw in the Roman concretes and improve the overall performance of our materials? Now, the Romans didn't have our fancy technology. They had to use, well, shall we say, old-style reactors to do their chemistry. And what they did, and these bad boys are very good at doing two things: dehydrating and decarboxylating materials. The Romans knew that if they didn't understand the chemistry, but if they took some of these materials, they greatly enhanced the durability and resilience of those materials. Reactors. The reactors are very well understood. The bottom row is basically the chemistry that's taking place, and then there's an evolution of the reactors all the way to modern-day rotary kilns. These kilns are very efficient and very well integrated in terms of the energy uses that they have. But I'm open to any suggestions that people may have on how to improve them further. If we change some of the composition up front, maybe we can do something at the kiln level too. And third, is there a biogenic pathway for what is going on? Biologists and geologists have noted on certain volcanic islands in the North Atlantic that in areas of high microbiological activity, that not merely the calcite and the calcium carbonate materials produced by some of those things being studied right now, but rather a lot of those same minerals that the Romans observed in their cements are there as well. So the question is, can we get our little buddies to get their flagella together and play on the big kids team for once? So, the goal is clear. Can we increase the durability of the cements and do it in a way where we can leverage the existing infrastructure to produce a higher performance material at lower cost? The social benefits as a result would be manifold. In terms of a more efficient, a more efficient infrastructure leads to a more efficient economy, higher productivity, and a lower frustration level all around. And if we can manage to do all that, then maybe, just maybe, our ultimate personal desire can be met. And that is, we might be able to stop saying those bad words and make our mamas proud again. Thank you. You want this?
I don't think that we need that anymore. Thank you, Joe.
Sure.
Okay. Thank you to all the speakers. And here you have the numbers again for questions that you may have. And I have a few questions here. And they seem to be rolling the other way. So the first question that I have here is actually for Mario. And it's about the need for new methods of training for future engineers and scientists in order to really implement your concurrent control engineering approach. Is there?
Yeah, well, I think this is a great question, and there is a great need, to do so, because as I mentioned in my presentation, because of the much bigger complexity of the technology today, we have specialized, all the careers, and then we are missing this point, the big picture. So I think actually that we have a great need, of this approach at the university. So how to do so? Well, I think that we have to do this together, but it's definitely, something very important, and this will allow, companies to think in the future in another way as well, because with engineers trained in a way that is, with this big picture, in mind, will be easier, to work in this concurrent engineering way.
Thank you. This is a question for Joe King, and it's about how do you evaluate and demonstrate the performance and durability of these new materials that you have been laying out?
That's always a problem because it's a very conservative industry. And how do you do and say that accelerated testing is actually indicative of future performance? There are a number of methods that people use in weather chambers and using higher temperatures and things. But you can often tell from how rapidly the compressive strength builds and what sort of, if there's a ductile component to the materials as well. Roman cements have a slight ductility to them. Most cements are brittle materials, as you know. But it's a very difficult question, but it's also a critical question that we're going to have to answer when we put out our metrics.
For Victoria's, there's a question with regard to the membrane functional biofilms. What kind of growth substrates or supports would you envision for these type of membranes?
That is a really great question, and it's one that I'm not sure I can answer right now. I think that the mission with my particular fast pitch was to throw out some really crazy ideas of what we could potentially do with synthetic biology. And I think that there's a lot more work that really needs to happen. I can envision combining biofilm growth with some kind of other scaffolding or templating. Perhaps that's the method that we need to go down in order to make this an actual practical way of making films and membranes for separation technologies. I think that many of you who work in synthetic biology probably have ideas that could better answer this question. So please let me know.
Thank you. So, question for Joe. Cornelius, what are the biggest challenges that you envision for deploying the distributed sensor systems in agriculture?
You have an hour? Actually, it's an area that precision, actually, if you go back 25, 30 years, this has been a holy grail from an agricultural standpoint. So there actually is a long history of challenges in this particular space. Obviously, each one of those components carries with it its own set of challenges. Starting off with sensors, for example, making sensors that are low cost, biodegradable, ability to be deployed on a broad scale. If you look at computational capabilities, again, ability to actually make them inexpensive, robust, and able to work in very harsh environments with a high degree of accuracy. The power systems obviously are incredibly challenging. We're in very remote areas, and if we're looking at sensors that hopefully we can deploy much more diffusely, that probably translates into moving into entire new power systems. And computational analytics. I have relatives that have been collecting precision ag data for the last 20 years, and they have 3 ring binders that are just surrounding the room because we haven't actually been able to harness the knowledge and the insights that are in those data sets. So when we start looking at not only our ability to collect information, but our ability to actually move that information from very remote locations to hubs that actually allow us to process it into information that actually translates into a management decision. And oh, did I say that we want it immediately?
Okay, thank you, Joe. People are really interested in concrete, so I get a lot of questions.
It's fundamental.
So the one question that is asked, one participant is asking, how can we incentivize the use of more durable concrete if the short-term cost is higher?
Well, that's one of the things I didn't get into. The O&M costs of managing even existing concrete structures now often dwarfs the initial upfront investment. The problem is the people usually building something in any part of the construction industry are not those chartered with maintaining and managing it. And as a result, the two winds don't always talk. To piggyback also on the first question that was asked, I have a workshop coming up where a lot of experts from the Army Corps of Engineers, Department of Transportation, Bureau of Land Management, the people ultimately responsible for managing the infrastructure, will be there with the manufacturers and a lot of the lead scientists from national labs and academia to discuss exactly how best to marry this up. That gap is well known, but it's underappreciated unless you're the crew that's responsible for managing and maintaining the infrastructure. I don't know if that answered the question.
Good. Mario, what energy technologies have the greatest need for concurrent design?
Well, I think that it's not just only energy. This is an idea that can be applied to, all across engineering, specifically energy, and I'm going to ask the question, but I would like to ask, to say first that this is something very generic and it's very horizontal. Now, in energy, I think that there are many different examples. For instance, if you look at wave energy, for instance, the way that you design a wave energy converter is actually thinking in the dynamics and the control up front, because it should be a system that has, a maximum resonance, at the frequency of the waves that are coming. So you have a system that is changing the frequency. This is, actually a control concept. So this is an idea, but it's not only, wave energy, is renewable energy, is conventional energy, is the grid as well. You can design microgrids in a way that are more reliable against control problems and stability problems, in voltage control and frequency control, and this is the grid. We talk, about two examples in wind energy, another one in water treatment plants. There is another area, that control is key, and the design of the system with control, like anaerobic digesters, that you push the bacteria in a way that are just in the limit of being unstable. And if the system is unstable, eventually, the bacteria, died, and then you need, some months, to have the system running again. So then control is an issue there as well. As you see, is something, global, is horizontal, is affecting many, many different technologies. So I cannot say that it's one technology. I think it's all across the spectrum.
Okay. Thank you very much. This, I think, was a good closing round, and I wanted to thank all of you for attending this session.